they're probably some of the oldest life forms that there are on this planet.
I think it's better if we don't challenge them, you know. I think we should be good friends.
They can colonize and exploit all parts of the planet.
They have means to survive in a more efficient way than we do.
If we have a white froth, that is indicative of death.
They might be a little bit uneasy about having a process they can't control 100%.
All through the 10 years experience I've had here, we've not had any single health problem.
They are not in a hurry. We are in a hurry.
It's an area that we have to be very, very aware of.
Because environmental legislation is getting much stricter.
What exactly is causing all this?
It's a biological condition. It's something produced by life.
We're no longer prospecting for gold, we're prospecting for microorganisms. They change the history of our planet. They've caused the evolution of the planet, and they continue to do so.
We human beings like to believe that it is we who are in charge. But in actual fact, we're surrounded by tiny little organisms that make life on our planet possible. If they were to disappear, we and many other species would become extinct. This soil contains more such organisms than there are humans on Earth. Most of them are harmless, but some of them can cause dreadful diseases. We're of course talking about bacteria.
This planet of ours has been a bacterial planet for far, far longer than it's been inhabited by ourselves as animals or even by plants. So they have learned to use the natural resources of this planet.
Throughout evolution, bacteria have proved to be amazingly adaptable and able to exist virtually anywhere, even in contexts too hot, cold, salty or acid for other forms of life to survive in. Their properties have been applied in important tasks such as water purification and clearing up after oil disasters. And for thousands of years, we've benefited from their ability to decompose minerals. This remarkable place is Rio Tinto in southwest Spain. But the environment here is so hostile that I might as well be walking on Mars. Rio Tinto is located in the middle of the Iberian Pyrite Belt, where the bedrock is rich in sulfur. For thousands of years, natural processes and industrial mining have created an environment which is highly acidic and full of heavy metals. The streams are red from rust, a color that pervades the entire landscape. You rarely encounter any animals here, and the vegetation is sparse. But there are plenty of bacteria, and they're thriving. The question is, how do they survive? Obviously, bacteria are too small for us to see them, but the red color of this water indicates that they're here and that they're working hard.
The bacteria that they live in associated with minerals, they live on minerals. I mean, what they do is they obtain their energy from oxidizing minerals. In the reaction of oxidation, they can get the energy that they need to procreate, to walk around, to move, etc. In addition of water, which needs to be there, and mineral, which is the sort of energy, all the rest they take it from the atmosphere. So it's an interesting model, very basic model, probably very much related with the type of bacteria that they started life to progress in the earlier Earth.
Biomining bacteria are quite different from most. For a start, they have a requirement for strong acid. They're called acidophiles, which just means acid-loving organisms. So they need acid, they live in acid, they make acid. But the other thing is that the most important of these are bacteria, and these other archaea, which break down minerals by oxidizing using iron or sulfur as their energy source. So they're acid-loving and they break down minerals. Another word that is used often to describe them is lithotrophs, and lithotroph means a rock eater. So they actually can eat rocks, and you can actually see this if you go to the right environment. The bacteria have actually degraded, destroyed the rocks.
Energy-rich ore can be oxidized without bacteria, but microorganisms make the process several thousand times faster. Using oxygen from the air, the bacteria extract metals from the ore. This releases energy, which they use to grow and to multiply. The metals become soluble in water, and Rio Tinto was among the first places in the world to exploit this phenomenon to benefit mankind. The oldest metal objects found here date back 5,000 years. The question remains, who made them?
Historians don't agree upon the characteristics. Probably they were all chalcolithic Iberians, that's what is in the books. And the next cultures that are well established that they were operating here are the Tartessians, because they have several references in the Bible. And it seems that King Solomon was very kind of his metallurgic abilities. And also after that, Phoenicians, I mean, there was a lot of fights to dominate this mining area, probably because it was considered important. And finally, the Romans, they were here around the 1st century after Christ's death, and they were here for 400 years, and there was a big mining operation.
Slave labor was used to provide the Roman Empire with iron, silver, gold, and copper. In the mines, the working conditions were inhuman. The slaves lived and worked in total darkness, chained to the rock face. At most, they survived for 4 years. After the Romans came the Visigoths, the Moors, and then the Spanish. But it wasn't until the end of the 19th century that full-scale mining was resumed in response to the huge demand for metals created by the industrialization of Europe. The mines at Rio Tinto were taken over by the English, who abandoned bioleaching in favor of roasting. In 6 months, they were able to extract the same amount of copper it previously took 3 years to produce. Ore extraction methods became more brutal as blasting was used in open-pit mines.
Open-pit mining is a little bit environmentally crazy, because what you have is to remove everything. I mean, the mineral is sitting in the middle of a mountain, and what you have, instead of making a hole and trying to get there, you just remove the mountain and you put it someplace else. So you end up with a big hole that then the water table regains against the level and becomes an acidic lake, which, because it's acidic, has metals in solution, so it's a kind of environmental hazard.
The new methods caused other problems as well. Toxic sulfuric fumes from the roasting made the miners sick and killed off all vegetation within a radius of 20 kilometers. In 1888, the miners and local farmers had had enough and organized what is considered to be one of the world's first pro-environment demonstrations. It was put down by the military, who killed 200 men, women, and children. As a result, bioleaching was reintroduced a few years later, but the golden age of Rio Tinto had faded and the mining operation was soon closed down. Today, Rio Tinto and its bacteria is once again attracting interest, of an unusual kind. That bacteria possess a vital force strong enough to survive in outer space became known in 1969. The crew of Apollo 12 had retrieved a camera left behind on the moon by an unmanned space probe 2 years earlier. The camera contained perfectly sound individuals of Streptococcus mitis, a bacteria commonly found in the nose and mouth. The space scientists were intrigued by the discovery. If such bacteria could survive on the moon, mightn't there be similar forms of life on Mars, a planet quite similar to our own? And could studying the conditions at Rio Tinto provide us with clues about how such life came about?
Rio Tinto is considered an interesting and good geological analog of Mars. And the reason is because they start to describe the mineralogy of Mars, and in a very specific part of Mars called Meridiani Planum, they found minerals that in Rio Tinto are produced by the biology activities. It's just opening windows. I mean, that there is a place on Earth that there is this type of biology that produces this type of mineralogy, obviously it gives you some connection.
At Rio Tinto, the space scientists can expose their instrument to conditions similar to those in space. And the bacteria might just help the biologists solve the mystery of life on Mars. But here on Earth, the bacteria are already engaged in advancing development. Nowadays, metals are so universally employed we take them for granted, and the global demand is rapidly increasing. In the West, consumption is 10 kilos per person and year. The corresponding figure for China is only 2 kilograms. China, however, accounts for nearly all of the increased demand for copper. Russia, Brazil, India and Indonesia are also growing rapidly and in great need of metals. Countries all over the world are literally being hoovered for ore deposits.
The question is to know how to find new resources, and especially to be probably less dependent on importation of these metals. So there is a new interest in producing metals in Europe because of that, because of the pressure that has been now imposed by the high demand of the emerging countries and their needs in metals.
Europe was one of the centers, the first centers of industrialization, and consequently has a very, very historically well-developed mineral processing, metal fabrication, metal forming business, and is one of the world's largest consumers of metals. Europe, unfortunately, was not as blessed with mineral resources as were certain other places in the world, like South America, Africa, Australia, and most of the easily accessible, lower cost, higher grade minerals have been depleted in Europe.
In Europe, there is a number of small and medium-sized ore deposits which still haven't been touched. So far, they haven't been considered worth exploiting using ordinary smelting processes. Europe also has large quantities of mining waste with a metals contents that frequently exceeds that of recently located ore deposits. These metals could be extracted using new methods. And one such method is bioleaching, which employs bacteria like those in Rio Tinto.
To use the good bacteria, the good microbes, in order to promote reactions that are interesting for us, I think what we need is to learn why they do it and to favor the conditions that promote these type of reactions. So in this specific case, these bacteria are able to oxidize metals from minerals. They solubilize the metal so they can be easily extracted. Well, we have to understand why they do it, how they do it, and then to try to devise the engineering management in order to, they will have their share and we will have our share.
Wherever waste from the mining industry is deposited, there is a risk that metals and other elements will seep out and harm the environment. By recycling waste heaps, you can improve the environment around the mining site. This must of course be done using methods that do not in themselves contribute to any seepage. And this is especially true in Europe, which is so densely populated. BioMine is a research project where scientists from 14 different countries are investigating how bioleaching may be used in Europe.
This project, the interesting thing is that it helps to develop technologies which are more environmental friendly. So what we want to do is green mining, so to say. And this is exactly fulfilling the objectives of the environmental policy of the EU, of the energy policy of the EU, to try to be greener.
I think the spirit of the BioMine, it's just a project just to rescue mines that have been abandoned, and probably with the old technologies they are not useful, or it will be very difficult to get the metals out of it. But using bioleaching technologies, probably they will be they can be profitable.
The work consists primarily of finding bacteria capable of leaching the complex, low-grade resources available in Europe. As such organisms frequently thrive in extreme environments, tracking them down can be quite dangerous.
Bioprospecting for these organisms is sometimes rather difficult. Some of the best sites to access these organisms from might be old mines. And old mines might be deep mines, so you have to go underground. And because the mines might be long abandoned, they're no longer, in some cases, that safe. So you have to be very careful. Certainly in geothermal areas, such as Yellowstone, where I've done a fair amount of work, the areas that you might find these organisms are not particularly stable in terms of their land surface. And unfortunately, there are incidents of people falling through geothermal areas and getting actually cooked.
But finding the right kind of bacteria is not enough. Time is money, and if extraction is to be profitable, the processes need to be fast. Bacteria, however, keep to their own agenda and refuse to be ordered about.
Bacteria do it because that's their way of living. So they do bioleaching not because they want to extract metals or they want to help you or they want mining companies to be rich. I think they do it because they are hungry and they want to eat. One negative thing that engineers don't like from bioleaching is that it's very slow. And the reason is because these microbes, they are associated with minerals, so with geology. And in microbiology, we call that they have geological time. So they are not in a hurry. We are in a hurry.
In this pilot plant in Madrid, researchers have developed a method to reduce bioleaching times. It's now possible for the first time to extract zinc and lead, even from low-grade concentrates. And the processes that used to take several days now only take a few hours.
A vital concern in the research work is to ensure that the bacteria thrive and are happy. Only then will the metals be effectively extracted and the process times short. We also know that bacteria are team players.
In the beginning, there was a steep learning curve. We thought for many years that there was actually only one organism that could do this. We have learned over the last 50 years that there are many organisms that can do the trick of breaking down minerals and helping the recovery of metals. And that microorganisms, when they work together rather than work in isolation, are far better. There are probably about in excess of 20 to 30 different organisms that can be involved in the process.
So far, we've seen that bioleaching works very well in warm climates. But since many of Europe's dormant ore deposits are located in the Nordic countries, the aim is now to get the bioleaching processes to work in cold climates as well. In this, the experts have made major advances.
The microorganisms we've been working with have been low temperature microorganisms. So we have found them in the north of Sweden and the north of Finland, the north of Russia. So these microorganisms are what's called cyclotolerant. So they are able to grow at the low temperatures. So in the winter, they will be able to grow better than many other microorganisms. Whereas in the summer, they're also able to grow in the warmer temperatures. Low temperature microorganisms are able to oxidize iron at about 80% to the rate that they can at 5 degrees than they can at 25 degrees, which suggests that even at low temperatures, these microorganisms are able to grow quite rapidly and to oxidize iron, which is the catalyzing step in bioleaching processes.
There are two approaches to bioleaching: stir tank leaching and heap leaching, as here in Finnish Talvivaara. Heap leaching is suitable for large quantities of ore that has a low metal content. It's inexpensive, and today it's primarily used for extracting copper. But here they're extracting nickel.
The newly opened mine at Talvivaara has ore enough to last at least a quarter of a century. The 33,000 tons of ore mined annually is ground into particles measuring less than 8 millimeters. These are then deposited in enormous heaps, which give the landscape its special character. The next step is for the bacteria to get down to work.
They are part of an industrial process, but they haven't been put there. They are found there naturally. So this is not in the sense of man using microorganisms. This is man exploiting natural microorganisms that are found in the environment.
The bacteria-laden leaching fluid trickles down through the heap. When oxygen is pumped in, the process begins. The bacteria start eating the ore and the metals are leached into the fluid. As the process continues, the conditions in the heap begin to change.
In the cold climate, our heap produces quite a lot of heat. But in our case, I'll say that the most important question is: are there enough thermophilic bacteria in this ore?
In a bioleaching environment where this is being done for a commercial sense, you will get gradients of temperature, where the middle of the heap will be very warm, up to 40, 50, 60 degrees centigrade, whereas the outside of the heap might be minus 30. So there you will have a continual gradient from the plus 60 all the way down to the minus 30. And through that gradient, different types of microorganisms that are adapted to those temperatures will be able to grow. Bioleaching will occur with different minerals at different rates. And this sometimes means that different metals will come out at different times. So what might occur is that you would do a primary or a secondary leach, whereby you would turn the heap over and rebuild it so that the further, more difficult metals would then come out at a later stage.
Heap leaching processes are difficult to control and take quite a long time. Although bioleaching is a relatively new approach in Europe, the new plant at Talvivaara are expecting good results.
We will be very competitive in the international market. This ore, the recoveries are extremely good.
Bioleaching methods are already applied in many parts of the world. Full-scale production plants are in use in China, in Australia, and countries in South America. And there's also one here, in Kasese, in southwestern Uganda.
Early 50s to late 70s, there was a copper mine producing copper up in the valley about 12 kilometers away. It was one of the biggest copper mines in East Africa at the time. And they dumped their cobalt-rich, their pyrite stockpiles just on this high ground above us here.
The waste material was known to contain valuable cobalt, but there wasn't any satisfactory method of extracting the metal. So therefore, the waste, almost 1 million tons of it, was simply placed in stockpiles just like this one.
The mining waste in Kasese consists of pyrite, the same sulfur-rich material as in Rio Tinto. The bioleaching takes place in huge tanks, but unlike similar plants elsewhere in the world, the extracted metal is not gold.
The main reason why this plant was started was to extract the cobalt. However, within the pyrite we have other elements. We have copper, we have zinc, we have nickel. Those are some of the major elements we find in the pyrite.
Cobalt may sound like an unusual metal, but is in fact used in aircraft engines and in rechargeable batteries for laptops, cell phones and many other technical appliances.
But the new emerging use for it is obviously the hybrid vehicles. I believe every hybrid vehicle uses about 5 to 6 kilograms of cobalt in its batteries. So that is a market which is going to explode. So hopefully there will be a big use for cobalt there.
But how are the metals actually extracted? As in Rio Tinto and Talvivaara, active bacteria exist naturally in the mining waste. In the leaching tanks, however, the aim is to get them to work faster and more effectively.
It's important for us to ensure that the bacteria have the optimum conditions of growth, because the more the bacteria, the more the oxidation, and the more cobalt or other more pyrite will be able to dissolve.
Conditions such as correct temperature, pH value, air and flow of nutrients have to be just right for the bacteria to thrive and do a good job. During the entire process, the engineers continually determine whether or not the bacteria are contented.
We normally look for a nice, like a coffee cappuccino color of a froth that is not really stagnant, but which breaks easily. That is a sign that the bacteria are healthy. Now, if we have a white froth, that is indicative of death, because the white froth normally comes also with a bad odor, which tells us that there's something wrong. And when we see that, we quickly go in and investigate.
The bacteria don't respond well to major changes. If all of them were to die, one would have to start all over again by fetching new organisms from the heap and cultivating them to tank concentration. Production would be at a standstill for 6 months until the processes were ready to start up again.
As a tentative measure to ensure that we don't get into such a situation, we have a small 1 cubic meter tank in which we keep a live bacteria growing, and we re-inoculate every month. So that small 1 cubic meter tank gives us enough bacteria to ensure that we can restart in any case we have a problem.
Working with bacteria means you've got another extra couple of million employees to keep happy. And that's difficult because they have to be fed and oxygenated, and they have to be kept in good ambient conditions. And as soon as they get a little bit unhappy, they let you know immediately.
You may think that sometimes the bacteria are no more active at all, and you may panic, for example. And well, what we have learned here is that the process is so robust that you may be totally confident that at any time it can recover of almost anything, I would say.
Just across the road from the bioleaching plant lies Queen Elizabeth National Park. And here you'll find a mosaic of different habitats, and the wildlife is extraordinary. Interestingly, having found a way of extracting cobalt from old pyrite stockpiles has actually improved the environment in the park.
The mining operation at Kasese was closed down in 1980, leaving the heaps to be exposed to wind and weather.
The pyrite stockpiles just on this high ground above us here. For 30 years, when you get sunshine, rainfall, you get acid water generation, heavy metal runoff. So for 30 years, the acid water and heavy metal contamination is running down this slope and into Lake George, which is about 10 kilometers that direction. So yeah, it was a huge environmental issue.
That water used to flow because it's a hill, and the national park is in a valley, is in a rifty valley. So it used to flow easily, washing and killing everything it came across. It was much. It would be a big. It was a big volume. It would wash away It eroded actually. It would erode and destroy.
In 1993, when the project pilot started, there was a berm, a wall built, which contained the stockpile, and all the runoff was collected in this dam here, Dam A. So it stopped runoff to the park and to the lake.
But after that, there has been progressive regeneration of plants. Even if you walked along the Pyrite Trail towards the lake, where stormwater flows, because we still have stormwater from other areas in the mountain, in the hills, which flows to Lake George. But along that path, you can see grass growing.
So no acid water is allowed to pass from this boundary into the park. And it's had a very positive effect on Lake George. Lake George was at one stage an endangered Ramsar site, and it's no longer. So that's been a very positive effect.
Reworking the waste heaps at Kasese has not only addressed old environmental issues. The extraction of metals is profitable. The question is, can the approach used here also be applied elsewhere in the world?
The most important result of this project are that it has shown that biotechnologies could be applied to European mineral resources in a sustainable way, economic way, and that it would have effectively limited impact on the environment.
European mining companies are being pressurized by increasingly tough environmental legislation to upgrade their conventional smelting methods. Facing dwindling resources, the companies will also have to keep an open mind when it comes to finding new ways of meeting future demands.
The most important part is that what we are learning is that bioleaching technology is allowed to recycle very easily metals. So this means that we might not need to open new mines, just to manage the ones that we have in a proper way and then recycle all the metals that we are using. I think that's the combination of both bioleaching and recycling, using probably also live systems, organisms. It's the future of this field.
Bioleaching and recycling of metals may well become important tools in the metals industry of the future, not least in providing the entire sector with a much greener signal. Despite this, the mining companies appear reluctant to fully implement the method.
We know that the technology are there, it's working, but it also has to be feasible from the economical point of view. And that means that we have to increase recoveries, or we have to increase productivity in some cases.
If Europe wants to be as self-sufficient as possible in some of these key metals, then it's going to have to turn to these type of technologies such as bioleaching to cost-effectively extract metals.
So I would say Europe is in competition with the rest of the world in this field. And if we are not able to catch up quickly, there will be a gap between Europe and the rest of the world.
Thousands of years ago, when the Romans leached metals at Rio Tinto, they had no way of knowing that they were being assisted in their search for wealth and riches by microscopic organisms underground. Nowadays, we know much more about these stone-eating bacteria. We have learned to create environments in which they thrive, and we know that they like teamwork. And if we get to know them even better, we might be able to use them to extract metals for us on their own and without harming the environment.
Oh, the microorganisms are the boss. Nothing would work without them.